For this Wronskian problem, I don't have a differential equation, but we are going to look at kind of where the theorem doesn't say anything about the outcome of the Wronskian. So right here, to read really carefully, what interval I does the Wronskian of these two functions, y1, y2, guarantee y1 and y2 are linearly independent. All right, and here's our two functions, y1 equals x squared and y2 equals x times absolute value of x. All right, so if we compute the Wronskian of x squared and x times absolute value of x, that's going to equal the determinant of, we have x squared here, we have x absolute value of x. Here we'll have 2x. That part's a little bit harder, the derivative of x absolute value of x, so let's just work on that up here. So if I look at x times the absolute value of x, that's going to equal, it's going to have two different definitions depending on if x is positive or negative. So here I'll do x is greater than or equal to 0, and here I'll do x is less than 0. If x is greater than or equal to 0, then x times absolute value of x is just x times x, so this is x squared. If x is less than 0, then we get x times negative x, so we actually end up with a negative x squared. All right, what if we want to look at then x absolute value of x prime? Well, if we do that, we can take the derivative of both of those. So that's going to be 2x. This is going to be negative 2x for x greater than or equal to 0. This is x less than 0. But another way to write that is just 2 times the absolute value of x. Right, if x is greater than or equal to 0, I get 2 times a positive number. If x is less than or equal to 0, I get 2 times a negative number, which all turns out positive. So it's equivalent to 2 times the absolute value of x. That's the derivative. So I'm going to write in here 2 absolute value of x. All right, well now we can compute the determinant. So I have x squared times 2 absolute value of x, so 2x squared absolute value of x, minus I have x times absolute value x times 2x. So I end up with 2x squared absolute value of x. And that's going to equal 0. So now the theorem doesn't say anything. Doesn't say anything about the linearly independence or linear dependence of these two functions, x squared and x absolute value of x. Theorem doesn't say anything, it only says something when you have isolated zeros or no zeros inside an interval, and for this thing it's 0 everywhere, from negative infinity to positive infinity. So theorem doesn't say anything, so we're going to have to look a little bit closer. And if we graph these, we'll see that they are linearly independent from each other. So we have, here I'll have x squared versus x. That ends up making a parabola, something like that. And here I'll graph x against x times absolute value of x. That'll make a parabola that looks like that. And right, so there's no way I can multiply this function, x times absolute value of x, by a constant to get this function over here, x squared. So even though the theorem didn't say anything about the linearly independence or linear dependence of these two functions, x squared and x absolute value of x are linearly independent. All right, so just that's the fine print of the theorem. If it's equals 0, you don't know anything at all.